Is that working? Yeah, okay. Okay, great. So thanks, Brendan. We're going to start with the first lecture. This is Alexey Nesvizhskii from the University of Michigan, Department of Pathology. So Alexey has been a force for good in computational proteomics for a long time, and in the last few years he's become very interested in the analysis of DIA data, but you're going to see he does it a little bit differently from what you've heard so far. So please, Alexey, we're looking forward to the presentation.
Well, thank you so much for the introduction, and thank you for inviting me here. I like, is it okay? It's a weird feeling wearing that stuff. So I like coming to Zurich in Switzerland. I think it's my third trip here this year. But my day started with a shocker. I was waiting for the shuttle bus to come here from my hotel, ETH bus, and I was 5 minutes late. I mean, it's never happened before. I think I'm concerned because once you take the Swiss precision away, sort of the country is going down. I mean, so what's left, sort of. So let me talk about DIA in the way I look at DIA data, and I looked at the lineup of speakers and those who talk about DIA before me and after me, and it's a very, very impressive lineup. So I was thinking, gee, I mean, what am I going to say that's going to be different or better than everybody else has to say about DIA data? You probably should know everything about DIA by now. It's in 2 days of DIA. So I thought I'll give you a few facts about DIA that maybe you didn't know before. So I was thinking sort of what other people think about DIA when they think about DIA, because DIA is different thing to a lot of different people. So I sort of Google, when in doubt, you always can go and Google something. So I Googled DIA, and actually DIA is a lot of different things, right? So DIA, for example, stands for the Defense Intelligence Agency. And what I liked about that is that their motto, and that's on their website, is do what matters, discover DIA. So I think that's exactly what we want to do here, right? We want to discover what DIA can do for us. So I really like that. So that's one thing. So DIA can also be fun. So it turns out that DIA is a Korean K-pop pop group, girl band. In this case, DIA is actually stands for diamonds, I guess, shortened, but the name of the group is DIA. So I went to a website, and I really like the quote from the manager of that group. You can read it here. So the meaning of the group of DIA, the meaning of the group name carries the hope that, like diamonds, they will be the most valuable of all jewels and will continue to receive love and shine even after time passes. So I'm hoping that sort of in a few years later, we'll still remember DIA. If there is something else better comes in the mass spec field, we'll remember DIA with love and shine that it has. Also DIA, so I'm in Michigan, in Ann Arbor, which is about 40 minutes away from Detroit. And I don't know, some of you here maybe from the United States. If not, you heard, well, I know Brandon is, you heard a lot about Detroit probably, right? As a place that sort of struggled a lot in the last 30, 40 years for various reasons. What you don't know probably is that Detroit also has a lot of great stuff that you need to discover if you're in the area. One of them is the Detroit Institute of Art. So that's why I thought, oh, DIA is an art. At this point, to some degree, it's still true that DIA is not a routine application. It's an art that you need to figure out how to do it. But it's really beautiful if you know how to do it. And this is a Riviera court. And I'm a big fan of Diego Riviera and his art. And this museum has a really nice sort of atrium with the fresco sort of painting by Diego Riviera. And the last thing that I found, well, that drew my attention, that was a concern, because DIA is also an island. It's an uninhabitable island off the coast of Crete. And I thought, wow, that's not a good omen, right? Because we want to be a DIA really widely used technique and not a deserted island. So that's sort of my thoughts about DIA that I thought I will share with you in the morning, thinking that maybe at least if you learn something new from my lecture, maybe that's what it's going to be. So let's try to make this DIA, a really hopping community and not a deserted island.
Alexey, back here. didn't Detroit have to sell off some of their art in their bankruptcy?
Fortunately, no. Yeah, so
bad?
Detroit was in bankruptcy as a city, which was the largest city in the United States that went through the bankruptcy process. And as part of that, the pension funds that were owned a lot of money and other creditors wanted to force the city to sell its collection. Fortunately, a few rich people stepped up and donated a significant amount of money. They also reached an agreement with the pension funds. Basically, the museum promised to raise something like $150 million over the course of 5 years to pay the pension funds. And I think that happened over the years, over the last 5 years. So the collection now is safe, and they sort of pay the creditors, not the full amount, but what they agreed to pay. So it's sort of safe. So if they had to sell something, it was just a minimal amount. But yeah, the whole museum was sort of, there was a possibility it would be for sale, not the whole museum, but the most valuable parts of it. So what is the DIA good for? I think it's a really great strategy. Well, first let's talk about what DDA is good for. I mean, that's a really great strategy, as we know, for a lot of things, especially for getting deep coverage when we have really ample sample material and mass spec time. We can fractionate, we can sequence, get really the deepest coverage possible of the proteome. The problem with DDA, as we know, is not that the number of proteins that you can identify, but the number of missing values that if you want to quantify across multiple replicates. There is a solution to that. I'll comment on that later, such as alignment across different runs, and then using AMT-like approach, accurate mass tag, which is now sort of the latest implementation of that, is this alignment between runs and max quant. So there are solutions to that, but still the hope is that DIA can do that sort of job of aligning and finding each peptide in every run better than DDA. In doing so, it would produce more accurate, more complete quantification matrices. And it can also have the ability to better quantify modified peptides, because instead of quantifying peptide as a whole, you can sort of look at site-specific ions and better localize and quantify a post-translational modification that may be present on that peptide. So DIA is still a discovery proteomics. There is no difference between DDA and DIA in that sense. So you could call DIA a shotgun proteomics approach, because you still digest proteins into peptides. That's still there, whether it's DDA or DIA. And it's a discovery method, because you do a sort of data acquisition in an untargeted way. So there is nothing targeted in how we acquire the data. In fact, I would even argue that DIA is more untargeted as far as data acquisition strategy than DDA, because you're really acquiring information on everything versus the most abundant peptides that may be selected for sequencing in DDA. So if nothing else, DIA is more untargeted, more discovery-based method than DDA. So the questions are, what are the best applications of DIA? And I'm sure it's discussed in the course. And whether DIA is really a cost-effective technique compared to competitive strategies such as TMT labeling, for example, where you can multiplex and label 10 samples and mix. And what are the optimal strategies for acquiring DIA data and the best ways to analyze data, but all tying back to this question of what biological applications DIA is the most useful for. Before I talk about what they asked me to talk about, which is the spectrum-centric analysis of DIA data, I also want to comment on the history of thinking about the DIA data, and I think this was how it was so far presented in the course, is that DIA is really a mass scan of all peptides that I agree with. This sentence I always make fun of. I don't know, do people still use that? That it's a permanent digital record of a sample. That sentence never made any sense to me, and I'm not afraid of pointing out that that sentence has no meaning. But that's what it is when you hear sometimes about DIA. And more importantly, the thinking about DIA was that it's a high-throughput SRM-MRM. So instead of doing just one transition, one peptide at a time, you can do it in a large scale in a high throughput way, but it's still SRM-MRM-like data that can be best queried using targeted strategies developed for SRM-MRM. So that's where the sort of purely targeted re-extraction strategies for looking at DIA data came from SRM-MRM field. So, and when you think about targeted analysis of DIA data, of course, the first thought was that you have to build spectral libraries for doing that, because that's what you do for SRM-MRM data. And these were the first strategies that we developed for DIA data analysis that were relying on basically building spectral libraries from DDA data and then interrogating DIA data using those spectral libraries, followed by sort of statistical analysis, protein level summarization of the peptide level results, and so on. And the tools that are that we developed, of course, you all know about these tools. So when we started working on this, I know 6-7 years ago, we wanted to do something different because, I mean, why would you do something that's already others are doing in a way pretty well? So we, on purpose, and because we felt that it was a really good strategy, wanted to look at DIA data as an discovery data that can be interpreted using untargeted direct methods to identify peptides like you would do with DDA data, and really put DIA data in the same workflow using the same tools even for downstream processing as DDA data. And also our thinking about this was that, and I want to present this part, I also want you to understand that I'm sometimes exaggerating this a little bit on purpose to make the statement. But, you know, if you don't want to exaggerate, you can say that, well, lessons from the history is that relying on previous knowledge in proteomics hasn't worked so far really well in many applications. So the moment you start sort of relying on previously collected data, especially if that data is old, 3-4 years old, that's no longer really represents what the current generation of instruments generates, and our sample preparation protocols change. So relying sort of on past knowledge as a way to do a data analysis of current data hasn't been very successful. And for example, one example is the Swiss 2D page database. Again, since we're in Switzerland, I thought I will mention that. That was an attempt to build a database, 20 years ago, of 2-dimensional gels. And then you take your new 2-dimensional gel. That was before sort of shotgun proteomics, when proteomics was gel-based. And then you map your 2-dimensional gel onto that library of 2-dimensional gels, where you already have each spot annotated to a particular protein from previous spot digestion and sequence identification. And then you basically identify what proteins you have in the abundance on your new gel. So that didn't work really well. In that case, of course, it also didn't work well because the technology of 2-dimensional gels is no longer used and sort of went away, but there were other issues as well. Or even just using spectral library searching in a more sort of thinking, a more familiar concept maybe for most of you in the audience. Even just using spectral library searching as a way to replace conventional database searching. That hasn't really worked well. The postdoc who replaced me at the Institute of Systems Biology, where I did my postdoc in Rudy Abersol's lab before he moved here, Henry Lab. So he sort of was sitting on my chair and he was developing spectral libraries at the time with the goal basically to replace database searching using spectral libraries. So people still don't use spectral libraries for conventional database searching for various reasons that we don't have time to discuss. All is this to say is that relying on previous knowledge, again, is not as successful as we all hoped it would be. So that's why we thought that if we can get rid of this spectral library generation step using external data, like previously collected DDA data, that would be really nice. Even if we generate spectral library using DDA on the same samples on the same instrument as part of our study, if we get rid of that, it would also be nice because we don't have to spend time and money basically doing DDA analysis prior to DIA analysis, right? If we can do everything just from our DIA data, that was at least save some time and money. So that was our goal with the project that we started. Now it's probably already 7 years ago. And I would say that it's actually worked out pretty well, I think. So the aim of what I'm presenting today in our strategy overall is that peptide identification can be done directly from DIA data without the need to build the spectral library as a first step in analysis. I will get back to that. There is still a value in building spectral libraries, but only as a second step. And this is where our hybrid computational strategy comes into play, is that we can combine in a smart way untargeted spectrum-centric analysis with targeted re-extraction and peptide-centric scoring for the most efficient analysis of DIA data. So the spectral libraries are still useful, it's just they're built directly from DIA data and not using DDA data or publicly available DDA data that's outdated. So the strategy that sort of we proposed has two components. So the main part of what I'll be talking about today is the left part here. but I will comment also on the right part here. So the left part is that basically the DIA data can be analyzed using spectral-centric strategies. You can call it direct DIA analysis or spectral-centric analysis or untargeted analysis, so that all means the same thing. An idea here is that you can identify peptides from DIA data directly. In our case, in our strategy, we do demultiplexing. We basically take DIA MS2 files, and then we demultiplex them to create what we call precursor fragment groups. I explained that later. Sort of MGF files, like in normal DDA data. And then we can search that precursor fragment group data against the sequence database using your favorite search engine, or even search against a spectral library if you wanted a spectral library-based identification, like with regular DDA data, to identify peptides using the spectral-centric strategy, and quantify as well, like you would normally do from MS1 or MS2. And that gives you sort of the outcome of the untargeted direct analysis of DIA data. Now, what we also proposed immediately as part of the same paper is that there is no reason to stop here, but what would make most sense, of course, is then to build a spectral library from these results, right? Not from some publicly available DDA data or from DDA data acquired on the same samples, but from DIA-derived identifications to build a spectral library. And then interrogate our DIA data using that spectral library, because that would allow us, using peptide-centric scoring, that would allow us to reduce the number of missing values that we would otherwise have here, because this is still subject to the same limitation as a conventional DDA data. We may find a peptide in one run, but miss it in the second run, find in third, miss in fourth, right? Because this is like a conventional DDA, basically. So to replace those missing values, we do have to do the peptide-centric scoring part. And that's what we propose to do, but using this library built from these results. Although, if you do have external library, publicly available DDA data, or you have sample-specific DDA data for which you build a library, you could, of course, merge that library with your spectral library derived from DIA data as well as an option. So that's the strategy that we sort of outlined, and that's a strategy that we are sticking to up to this point as well. Except I will tell you in this lecture and a subsequent lecture in a few hours how our thinking evolved a little bit over time about this strategy, but the basic concept that we illustrated on this slide remains the same. So let's talk about this untargeted identification and how we do that. So that idea here sort of derived from what Waters scientists developed prior to this work for a type of DIA strategy called MS to the E approach, where it's really like DIA data, but the MS2 is done using high energy fragmentation on the entire range of MOS values. So there are no windows. It's basically low high energy fragmentation. But the concept sort of is similar to what they were doing there. And the idea is that we could basically reconstruct from MS1 data, we can detect all features in MS1 data, like you would normally do with any search, with any strategy, whether it's DDA or DIA. You can do untargeted identification of all MS1 features that looks something like this, right? So all precursor ions could be detected. Now, in addition, in DIA umpire, we also do the same from MS2 data. We detect all features in MS2 data, including those that we expect to be present in this region that corresponds to the window for a particular MS2 scan. So MS2 scan is acquired using certain MOS range, right? And in that range, we have some unfragmented precursors in MS2 as well, right? So here you see that there is a band. That band in MS2 scan of DIA corresponds to that MS1 window that was the isolation window in MS1. So all of these signals here are probably unfragmented precursors that are left in MS2. So we can also detect them and combine with the list of MS1 precursors that we identified from MS1 data. So we have then the list of MS1 sort of precursor features that we derived from this and from these scans. And we can establish elution profiles for each peptide like you would normally do. So we have these extracted ion chromatograms, right, for precursor ions over time. And that's sort of how this data looks. we can go to a fragment MS2 data and then extract all peaks from this data, all curves, peak curves. And then you can ask the question, which peak curves here correlate in the elution profile with the fragment, with the precursors from here or from that segment that corresponds to fragmented precursors here. And then calculate the correlation coefficient between the fragments and precursors, and then assemble precursor fragment groups, which is basically for each precursors that we detect from here or from here, we have a list of fragments that have elution profiles that correlate well with the profiles of those precursors. So that's what we call precursor fragment groups. So there is a correlation coefficient, and it looks a little bit more complicated than that because for each precursor we have a lot of fragments that have a significant correlation with that. But the same fragment can correlate with multiple precursors. So we sort of have this precursor fragment graph that we apply certain heuristics to create a certain number of precursor fragment groups where there is one precursor and multiple fragments. So we allow, for example, the same fragment to be a part of multiple precursor fragment groups. So the same fragment can correspond to multiple precursors, and same precursor can have multiple fragments. These are actually parameters in DIU-Empire that when you do the exercise later, if you look at the input file, these are the parameters that you can adjust, how many precursor and fragments you sort of allow to have this relationship. I think by default, we allow precursor to have up to a few hundred fragments, and then one fragment can correspond to up to 25 precursors. So we are very, very liberal with how we create these precursor fragment mappings. That's why the file sizes that we generate using DIU-Empire are bigger than a typical DDA data, because we overpredict the number of precursor fragment groups. We don't want to be too stringent. We would rather overpredict for most applications, and that let the database searching and subsequent data validation steps to filter out the false positives, rather than be too stringent and then end up with too few fragments assigned to precursors, so our search engine cannot find that peptide identification. So that gives us what we call pseudo-MSMS spectrum. So precursor fragment groups, if you save it as a MJF file, is going to be like a DDA-like MSMS spectrum that has a precursor MOAZ, charge state assigned to it, and a set of fragments and the intensities. And for the intensity, we take intensity of the fragment in the data, but multiplied by the correlation with the precursor. So that's what we use as intensity in an MJF file that we generate based on this deconvolution process. So this is how pseudo-MSMS spectrum look like. So this is a DDA MSMS spectrum, and this is DIA pseudo-MSMS spectrum on the same peptide. So this one is noisier than this, and that's again because we allow more fragments to be included in general. So DIA data that we extract using our strategy, pseudo-MSMS spectra look a bit noisier than DDA data. But nevertheless, they sort of perform in a relatively similar manner as far as the properties in database searching. The distribution of scores, the modeling approaches are very, very similar. So that's why we apply conventional DDA data analysis pipelines to analyze this pseudo-MSMS spectra. So once you extract pseudo-MSMS spectra using DIU-Empire, you have MJF files, and they go through this database searching step, and there are a lot of search engines that you can use. We normally do, as I'll tell you later, MJF plus, Comet, and extend them at this point. But we are switching to our new search engine called MSFragger. But you can use any search engines that you like. And then once you're done with this, like you would do with DDA data, you would do false discovery rate analysis, protein inference, and so on. And there are a lot of tools available for doing that. For example, Proteomics pipeline, percolator, peptide shaker, all of them will do a certain type of modeling and then create a protein list with all discovery rates estimated using decoys or other strategies. And then you can filter it, say, using 1% FDR. And that's your sort of output from that pipeline. So it looks like really like DDA data in a way, right? Except you're replacing regular spectrum with DIU-Empire extracted pseudo-MSMS spectrum. For the false discovery rate estimation, just one comment here, again, how we do that. So from DIA, we extract precursor fragment groups, and then we identify peptides. And you can build a spectral library from that, as we'll discuss later. But really, this part, there is nothing new about that part. In our case, we are using a mixture model based strategy that we implement in a tool called Peptide Profit that basically models the observed distribution of scorers for the PSMs. If you have decoys, decoys can be used as a help to model this negative component, the false identifications here. If you have decoys, in that case, you can also use semi-parametric modeling because you don't have to specify the shapes of the distributions, but it's exactly the same that we would do with DDA data. You could then propagate it to the protein level, do protein inference, do, say, protein inference and FDR filtering at the protein level, and so on. So there is no difference in sort of how we approach. The output from this strategy would be, say, PepXML files, and if you do protein inference, say using Protein Profit, ProtXML files, or some other output formats if you use other tools. And that would be the input to the next step if you want to build a spectral library based on these results, and then do targeted extraction, again, from the same DIA data, but using that spectral library that you derived from that same DIA data, right? So that's why we call it targeted strategy for peptide identification, followed by a peptide-centric targeted re-extraction as a second step that I'll discuss later. Now, one thing that's, I think, important here, and it's important to think about DIA data, is that we have both MS1 and MSMS-based quantification. So now, I think probably when you hear about DIA and Open SWATH, you hear about MS1-based quantification as well, and, or at least the importance of MS1 data. When we were working on this, MS1 data was not used as part of DIA data analysis workflows. So, so now I think there is more understanding that that's really important, but for a while I had to convince people that there is really a lot of value in MS1 data. First of all, you can quantify peptides, even though you do DIA, you can still quantify peptides using MS1 precursor ion intensities like you would normally do. And in fact, there is actually pretty good correlation between MS1 and MS2 data that you have. And both MS1 data and MS2 data, as far as the quantification is concerned, gives the same correlation and the same sort of reproducibility across replicates. So on the left, I'm plotting two replicates, intensities of proteins in the first replicate versus the second replicate, where the protein intensity was calculated using top 6 peptide approach. So it's based on MS1 intensities of top 6 peptides per protein. And you see that it's a pretty good correlation. And in this case, I'm plotting protein intensity estimated using fragments. But for top 6 peptides, we look at top 6 fragments and estimate protein intensity by summing intensities of those fragments. And you see that the correlation between the replicates is as good as the correlation for the MS1, maybe only slightly better, right? So both MS1 and MS2 data are really valuable as metrics of protein quantification in DIA data. In fact, actually, if you can combine MS1 and MS2 into sort of a single quantification score, I think that will help to eliminate a lot of outliers here and would probably give the best quantification, but we haven't done that in our hands, sort of. Here, I think I wanted to mention that for MS1, we have different ways to do MS1 quantification. You can sum all peptides, you can use top 3 peptides, you can use top 3 peptides, but selecting the fragments, the peptides that are most frequently observed, and all of them sort of give slightly different results. So based on this analysis for MS1 quantification, a strategy that we use in DIA Empire when we use the quantification module of DIA Empire these days. For MS1, I think we typically use, I believe, IBAC. But for MSMS, we use this approach called top N. So we typically use top 6 peptides, and for those top 6 peptides, we use top 6 fragments. But not any top 6 by top, I mean fragments that also observed in at least half of the experiments in a data set where that particular peptide or fragment was identified. So we select the most commonly observed peptide and fragments for each protein. And then of those that we selected, we will look what are the most abundant as a whole across the data set as a summed intensity across all runs. And then we take top 6 fragments and peptides and sum them. So that's a strategy sort of that we came up as what worked the best for us for protein level quantification based on MS2 data and DIA data. So here I sort of jumped ahead a little bit into quantification. So I'm going to come back to the sort of identification and then revisit quantification later, I think. So also, yeah, so that's a little bit less interesting. Let me skip that here. I want to make another point about importance of MS1 data in DIA. Again, DIA, traditional thinking, it's all about fragments. So why MS1 in precursor intensity? And the knowledge of MS1 MOEZ values that we observe, precursor MOEZ values that we observe in MS1 scan. Why it's important? It's because it allows us to distinguish between modified and unmodified forms of the same peptide. If we don't have that information and we use a wide SWATH wide DIA window, for example, 25 Dalton as was initially used. So 25 Dalton, when you think about this, for triply charged peptides, translates into 75 Dalton window as far as the masses of peptides, right? So there are a lot of different pairs of modified and unmodified forms are present in the same window. Unmodified peptide in its oxidized or associated form or carboxylated form, all of that is going to be for triply charged spectra, especially with wide windows like 25, all of the spectra are going to be in the same DIA window. And there may be only a minor shift in the retention time during modification because some of these modifications are not really change retention time dramatically. So in the same window, in the same MS2 scan, you will have a lot of forms of that peptide, modified and unmodified. So having the knowledge of MS1 information, at least, of what MS1 precursors we have allows us to make a call that we have more than just one unmodified form. We have also modification forms and so on. Because otherwise, you're dealing with fragments, and you don't know if those fragments are the same, whether it's a modified peptide or not. I mean, there are fragments that contain modification, but there are a lot of fragments that are shared between the modified and unmodified form, right? So if you don't know that, and you only deal with the fragment data, you'll be sort of mixing modified and unmodified peptides in the same analysis. And really, you know, it's a big confusion. I think that sort of this whole thing is underappreciated a little bit at the moment. Another reason is in-source decay. That's also present a lot when you lose one or two amino acids. And those could also be actually present, again, depending on what amino acid you lose and what the charge state is. They can be in the same scan. And so on. So by having this MS1 data, you could resolve, because then you can visualize MS1 scans and you have precursors in there, and you can sort of get a better information about how many precursors you have in that scan. And if there is a retention time shift between them, you can sort of have a better ability to distinguish between two different precursors that may even have very similar mass. That's why I feel that using this MS1 information as part of that analysis is extremely important. And since I mentioned that, we have a tool called DIA, BATMAS. So if you're interested in quality control of your data, if you're interested in looking at how MS1 data or MS2 data and DIA runs look like as far as the raw data, and you can explore those features and see the mass accuracies, or you can zoom in on a particular region of the spectrum and see what's going on there. That's a really, really great tool. It's called BATMAS, really, really well described. We don't have videos. You know, we're not like Brandon and Skyline team. We don't do any of that stuff normally, but this is an exception. We actually have a video for that. So that's how it looks. You can load your raw file into this tool, BATMAS, and then you'll see this is retention time here, and this is MOEZ, or the other way around. I cannot see now. This is MOEZ, and this is retention time. And you can zoom in on a particular feature and see how it looks. You can see the profiles across retention time for the whole run, and so on. If you do DIA umpire analysis, you could also load the MS1 features detected by DIA umpire and overlay it with this raw data in BATMAS. That's useful for optimizing the parameters in DIA umpire. Or if you do XCMS, for people who do metabolomics, for example, they use software called XCMS for feature detection. You can load XCMS results and overlay with the raw data. If you have PepXML files or identification results in a tab delimited format. You could load them, and then you'll see where a sequencing event happened and whether the peptide was identified or not with high confidence from that event. So it's a useful tool not just for quality control of raw data, but also to get a sense of how efficient the tools were for extracting the features and for identifying peptides in the downstream pipeline. Another comment I want to make here is that I think PTM modifications with DIA umpire is also possible. So we don't do it normally. But we could take our DIA umpire results, MGF files, and instead of doing a conventional search where we use a narrow mass tolerance of, say, 10 or 20 parts per million for database searching, we could open up this to hundreds of deltons. And in that case, we will identify modified versions of peptides as well, directly from DIA data. We don't do this very often because it's still a little bit hard to interpret the results. Like I said, in DIA umpire, we are over-predicting the number of precursor fragment relationships. So doing open searching with DIA data is a little bit trickier, is trickier than with conventional DDA data. So for the conventional DDA data, we do open searching quite a bit now. But for DIA data, we could do that, but it doesn't work as well yet. We haven't figured out a good way of doing that. We can find, 50, 60% more IDs by searching MGF files extracted using DIA umpire using open searching. And a lot of those are going to be real modifications that we believe, but there is also a lot of other things that we think is noise. And due to the fact that we overpredict sort of the number of precursor fragment relationships, we're looking at how to improve that. But I would not recommend at the moment doing this unless you sort of have experience with this type of data. Another tool I want to mention from a different group that sort of thought about spectral-centric analysis of DIA data is called MS-split DIA. It's from UCSD, from Nuno Bandeira lab. So what they do is different from DIA umpire. They don't do direct identification in a way like we do. They look at DIA data, and they also require that there is a spectral library like SWATH Atlas or some other community-wide spectral library. So what they do is really generating a sample-specific spectral library by taking this data, matching against that spectral library, and creating a subset spectral library. Then that library is used for targeted extraction. So that's a key difference between MS-split DIA and DIA umpire. So it's still a spectral library-based tool. So it's a way to take a very big spectral library that maybe includes samples that have nothing to do with the samples that we're analyzing and constrain that big spectral library to something that's likely to be in a sample. So it's a pretty useful strategy if you're in a sort of spectral library-based mindset. The only thing is that it's also really tricky when you think about this strategy, because what essentially they are doing is they are doing, without acknowledging that, I don't think they realized initially that they're doing wide mass tolerance search as well as part of that strategy. Because when they search against the spectral library, and they don't use precursor intensity, they don't have that information, sorry, precursor mass, right? They don't do MS1 analysis. They essentially search, say, a 25 Dalton MS2 scan against a spectral library. So they may be matching fragments from MS2 scan to spectra in the library that are not the same peptides that they have in the MS2 scan. So they may identify, say, a modified version of a peptide that's present in a library without sort of knowing that. Or the other way around, they may have a modified peptide in MS2 scan, and it would match to the unmodified spectrum in the library if it's in the same window. So that's why when they did this analysis, they actually identified way more than any other tool. So here's a comparison that they were showing MS-split DIA using spectral library, SWATH Atlas, restricted to them to a sample-specific library. So this is what DIA umpire identified. It was the same as Skyline and PeakView, but this is what they identified way more than, say, all other strategies. And I think it's in part because they were, without sort of acknowledging that, they were doing this sort of semi-open search. And that's why they were picking up a lot more stuff. So whether it's a good thing or bad thing, whether you would want to do that or not, it's again, it's a good discussion. As far as boosting the number of IDs, that's good. But you have to be careful about the quality of quantification, because you're not really quantifying the peptide you think you're quantifying, potentially in that case. So so think about that if you want to use this M-split DIA for your preprocessing of large spectral libraries. So let's talk a little bit about targeted re-extraction. So I told you that the first step is, in our view, was always to generate to do the direct and targeted DIA analysis as a way to generate the spectral library that can be interrogated using targeted re-extraction strategies as a second step. And that's because we wanted to address the limitation of DDA data that's still present in untargeted DIA analysis, which is the missing values, right? And targeted re-extraction with peptide-centric scoring allows a reduction in missing values. So when you think about targeted extraction, but that's really well discussed in many publications where it is. But if you know what you're looking for, a particular peptide and its fragments and retention times, you can go to, say, MS2 data and find those fragments and do scoring of those fragments to confirm that they really coelute. And also you can go to MS1 data and really confirm the GC precursor in MS1. And then that gives you sort of targeted identification and quantification of that peptide. I know Mike doesn't like the word identification, but I sort of use them interchangeably with detection. So if you wish, you can say you can detect and then quantify this peptide using targeted re-extraction. So in my view, when you do discovery-based analysis, really peptide-centric and spectrum-centric are really two sides of the same coin, because it's either you start with a spectrum and then look for peptide, or you start with a peptide and look for all spectra to find the best match. The difference disappears when you do it on global scale, when you take every peptide in a library versus every sort of piece of your mass spec data where that peptide could possibly be located, and do this comparison, which way you go really doesn't matter so much. So when we talk about targeted re-extraction, we sort of approach that from the peptide-centric perspective. When we talk about initial analysis of data to identify what's in the sample, we talk about a spectral-centric perspective. So DDA, in that sense, is not any different, and they also use peptide-centric and protein-centric strategy. So this is, for example, MaxQuant, what it's doing. It has this match between runs strategy, where once you identify peptides, then you align two different runs to each other, or you align all runs, and then you transfer identifications from one run to another run if you didn't have the peptide identified in a particular run, right? So match between runs is the peptide-centric scoring part of MaxQuant when applied to conventional sort of DDA strategy. The problem is, of course, that in DDA, all you have is the retention time and mass-to-charge ratio of the precursor. And that's not enough information, in my view, to do this analysis in a robust way. So they claim that they can identify 10,000 proteins in a single-shot experiment, where if you actually look carefully, 30 or 40% of those IDs come through this alignment match between runs approach. But I have not seen a really rigorous description of the false discovery rate estimation for that match between run strategy when you don't have any MSMS information, like in DIA. So only based on the retention time, and this is what they do. This is MaxQuant match between runs. So the idea is that maybe you found this peptide in the first run, but not in the second run, but you can align them, and then you can transfer identification. So recently they extended this concept to building the library. So you can say you can build a library of those MOAZ retention time values from a really deep shotgun sort of proteomics profiling experiment, say based on tissues, and then go to other samples where you do single shot analysis even, and then you align it to this AM. So this is really equivalent to the AMT that Dick Smith was developing 10, 15 years ago, accurate mass spec strategy. So that's sort of now this library building is part of the MaxQuant environment as well. But as I said, I think we need to work more on figuring out what the best way to do false discovery rate estimation for this sort of analysis, because there is very limited information available to transfer information from one run to the next. In DIA, when we transfer this information, essentially, We have, for these peaks, we also have fragments. Now, we did not identify the peptide from the fragment in the first place, maybe, like if we used DIA umpire followed by untargeted analysis, maybe we didn't get an ID. But at least we have MS2 scan where we can find fragments and compare those fragments with fragments in the round where we think we found that peptide with high confidence. But here we don't have that information. So in the targeted strategy, that's sort of how we approach that. Again, to summarize this, we take this data here from the direct and targeted analysis of DIA data. We build a spectral library based on this. We supplement it with external spectral library from DDA data if available. And in my second lecture, I'll talk about how we do it, talk about more recent work. And then we go to the peptide-centric scoring. And then we have less missing values at that point. And quantification, again, can come from MS1 or from MS2. So either way. So you can utilize both or just choose one of them. So, and this is the quant workflow sort of visually, that once you build a spectral library, then you can go to the quantification modules, and we have our own quant module in DIA umpire, or you could use external tools such as Skyline, OpenSWATH, or Spectronaut. So when we developed this, we had a we made a guess, and I thought, and I turned out to be wrong. So I thought that we can build precursor fragment groups from DIA data, and once we build the spectral library, we don't need to go all the way back to raw data to extract the signals, that it would be sufficient to go back to precursor fragment groups that we already assembled and find those peptides in those precursor fragment groups. So we didn't identify that peptide in the first place, but once we found it in, say, in a different replicate, we can go to the pseudo-SMS spectra that we assembled here and find that peptide in there. So I thought that we don't need to go all the way back to raw data. So I turned out to be wrong, and not going back to unprocessed raw data is a limitation of the quant module of DIA umpire. So we still have more missing values than if we went all the way back here. We just didn't want to re-implement, OpenSWATH, Spectronaut, Skyline targeted scoring, because we figured, that part is already functional and exists. Why don't we try to go here? But the good thing is that this part still works reasonably well, and a lot of times it's sufficient. And if you really want to reduce the number of missing values, well, we can couple this part with these tools. There is nothing that prevents us from doing DIA umpire, MGF files, conventional unification, and then going to targeted extraction using other tools. So that's an alternative that's fully functional, and probably in the long run is a better strategy to couple DIA umpire with, say, OpenSWATH or Skyline or Spectronaut. So I'll talk about this, like I said, in the second lecture. This is the strategy that we are taking. In the last few minutes, I have about 10 minutes for this lecture. I want to give a few, again, in the second lecture, I'll give you a little bit more technical details, but the first one is more of an overview. So how well this strategy actually works in practice? So I think it works reasonably well. So especially if you have window sizes that's around 10, 15 Dalton wide. This is where we have a sweet spot for DIA umpire at the moment. So on this particular study that was published last year, we looked at DIA and thermo arbitrary fusion instrument where we used 5, 10, 15, 20, and 25 Dalton windows. And all data was searched with, whether it's a DDA or DIA, we had both DIA and DDA. We searched exactly the same type, the same pipeline, which was extendum, comet, MGF plus, MSGF plus, followed by TPP, iProfit, 1% for discovery rate. So all the comparisons are done basically apples to apples because we analyze all data in the same way. And what we found is that the isolation window for us in our strategy matters a lot. And the sweet spot for DIA umpire is around 10 Dalton. That's where we get the highest number of peptide ions identified compared to 15, 20, or 25 Daltons. Interestingly, when we go to 5 Dalton, the performance drops a little bit. And that's really understandable, because if you go to a really narrow window, but the instrument is not fast enough, like in this case, this was a MS2 range. MS2 scans cover the range from 400 to 1200. So if you use 5 Dalton windows to cover that range, the cycle time is really long. So you only have a few points per peak. So when you go to 5 Dalton and try to cover the whole range, we don't have enough points to really get a good correlation between fragments and precursors, right? And that's the whole concept that we have in DIO Empire, that we need to correlate fragments with precursors. So as we reduce the window, the complexity, there is a reduction in complexity of MS2 spectra, but we are still able to correlate precursor and fragments. So we benefit from having narrower windows. But if you have a window that's too narrow, then the performance drops. If we generate windows, if you use narrow window but not covering the whole range from 400 to 1200, but you do sort of this gas phase fractionation, that's what I think David Goodlett called gas phase fractionation in the early days, where you do like a, say, 100 to 200 Dalton range of MOAZ values. I believe Mike is probably doing something like that as well these days, where he's using narrow window of like 200 Daltons and covering that with narrow windows, DIA windows. In that case, the DIA Empire, for example, should work just fine, because you have enough points to cover the MS1 peak and MS2 peaks and then correlate. But if you do the full range, that's where it sort of performance drops. So that's one caveat. So you wouldn't want to go to a very, very narrow window while trying to cover the whole range of values. Also, I wouldn't, the protein level, again, the 10 Dalton is sort of gives us the optimal results. We get slightly less in this particular case at the protein level than DDA data, although we get more at the peptide level than DDA for the same runs. But at the protein level, we get as much or slightly less number of proteins identified. In a more recent data, we are able to get with DIA more than what we can get with DDA. So this is a little bit outdated data. But sort of the 10 Dalton window is still optimal. Now, we actually don't use 10 Dalton windows, we use variable windows. But they are sort of somewhere in the range of 10 Dalton, 7 to 8 Daltons in the most crowded region. So sort of 10 Dalton I refer as a sort of the optimal, but you could sort of use variable windows where you can stretch some regions and expand in other places. But I also would argue not to look at these numbers overall, because it doesn't really matter how many proteins you identify here, because again, the advantage of DIA is not to give you more proteins, but to give you more complete quantification matrix. So whether you get really more than DIA than DDA or not, I think is a secondary question. What we also discovered is really that external libraries, as expected, are not really complete. This analysis was done using HeLa cell lines. And if you go to something like a pan-human library that was built using data sets that include HeLa cell line, but also a lot of other similar cell lines. So when we did our analysis here and we used DIO Empire, extracted MGF files and identified peptides, or for DDA data as well on the same samples, we actually identified a lot of peptides that were not present in the pan-human library. So even though we talk about HeLa, that should be well represented in that library, there is still a lot of new stuff that you can identify from your sample-specific HeLa runs. So the pan-human library includes HeLa data, yet it's far from complete. So if you go to samples that are not HeLa samples, the overlap with any existing spectral library is going to be lower. Of course, you can make bigger and bigger libraries, and the overlap probably is going to be better, but then you start getting into other issues that if your spectral library is so big that it's sort of a proteome-wide, the difference, really the advantages of searching against the libraries also sort of start disappearing as well. And you have all the problems with false discovery rates and so on. I think Isa probably talked yesterday about this very important consideration of the size of the library search versus what you actually expect in your samples, right? So, and also another point is the DA and DIA are really complementary. So if you're not looking, forget about the overlap with the library, but just look at this circle versus this circle, what we identified in DIA versus DDA. you see we find a lot of peptides in common, but we also find a lot of peptides that we only see in DIA and we only see in DDA. Of course, this is just 3 replicates. Perhaps if you had many more replicates, the overlap would improve, but it would not be perfect even then, because, for example, DIA has singly charged peptides that we're typically completely missing in DDA. So DIA always gives you something that DDA doesn't give you, and the other way around. But it's not only about singly charged peptides. There are a lot of other peptides that for some reason we can find only in DIA, not in DDA. We can go into more discussion to this in some other time. Now, what about the missing values? So we used the data set described in this publication where there are multiple replicates of the data on those liver microtissues. And we used DIA pattern, and again, we identified using DIA more than what they reported actually using Spectrum-Centric and spectral library-based strategy in the original publication. But the thing is that the number of missing values, that's what I want to make point in these slides. And with targeted re-extraction in DIA pattern quantification module, we significantly reduce the number of missing values that we had across different samples in this data set. So indeed, the targeted re-extraction significantly improved quantification coverage, less missing values. For example, in DIA, we went so we had 70% or 80%. So this is, I guess, peptide quantification coverage. And this is DDA and this is DIA after targeted re-extraction. So you see we do significantly better as far as the number of missing values across the data set in DIA than in DDA. So that's great. But when we compare it with what they reported using Spectrum-Centric as far as the number of missing values, even though we had a significant improvement in our strategy compared to where we started using targeted re-extraction, we did not get anywhere close to the number of missing values that they reported, which is almost no missing values using targeted re-extraction. Now, I would leave it up to them to sort of defend really this plot, because I think that's a little bit too good to be true to have almost no missing values at all. But the point is, and it's true, that by going back to the raw data, we are able to extract peptides more effectively. So that's why targeted extraction using DIA pattern has more missing values than if you take that library and put it in a Spectrum-Centric or Skyline open SWATH. So I think, if you were to take this library and then go to these external tools, we would go to, 90% or something like that coverage. So only 10% of missing values across the entire quantification matrix. So I already made that point about peak shapes. One comment that I wanted to make is that why, again, for 5 Dalton, our strategy doesn't work, and it works well for 10 Dalton or 15 Dalton, is that as we reduce the window size, we get less number of points per peak, and adjusted 5 Dalton in that particular way, we queried the data. We just didn't have enough points to do that. So it's not really the size of the window at all, where sort of this targeted, where this untargeted strategy of DIA part works or doesn't work. It's not the number of, it's not the size of the window. It's simply the number of points per peak that we have. So it's all about the balance between the scan time and also data accumulation, ion accumulation time, and some other things. So anyways, that's what we have here. So we are now sort of using 10 Dalton-like settings, but as I said, typically variable window settings. And the DIA pattern in that case work pretty well, actually. So we get very close numbers to which you could get using fractionated libraries built using DDA data and targeted re-extraction as far as the number of proteins identified and peptides. And a little bit less if you use the quantification module of DIA pattern. I will follow up on that more in the next lecture when I talk about a little bit more about details of some of the settings. I will get back to that. So I ran out of time, but I wanted to make a point where, let me give you just 1 minute before, extra 1 minute, that a lot of other people find this strategy useful. So for example, Birgit Schilling and Jesse Meyer from Buck Institute, they shared the slides with me. And I sort of collaborated with them a little bit. I helped them, but it's really they work they use this untargeted strategy for PTM analysis, where what they do is, and they do a lot of different stuff. I don't have time to talk about what they do, but they looked at, say, in this case, 6 dietary regimens for these mice, and so 12 conditions in total. And they want to do quick, accurate, and comprehensive quantification of post-translational modifications such as acetylation. So what they found that worked really well for them is to use DIO-Empire and really build a spectral library. Either it's for global proteome profiling or for the PTM-enriched samples. They basically used DIO-Empire to build pseudo-MSMS spectrum, and then used these research engines, like I mentioned, and TPP, iProfit, Protein Profit, and then filtered at 1% FDR, and then they took it to the Skyline for the quantification of PTMs. So, so on Skyline, you could sort of visualize the PTMs and the fragments, so that was really useful to them to have this ability to quantify specific fragments. But the point that I'm trying to make here is that really they found that untargeted analysis is pretty useful, and if you want to learn more, actually there is a paper that's coming next week in Nature Methods on that strategy. So, and that's again DIO-Empire followed by 3 search engines, and then this, and then building the spectral library and going to Skyline, and then doing PTM localization and reporting, and also using MapDIA. I'll mention this in the next lecture, for selecting fragments for quantification across multiple runs. So I think that's very useful, and in general I feel that PTM analysis, like I said, this is where DIA data has advantages, and I hope that sort of this is useful to them. Well, this is obviously useful to them, but I hope it's going to be useful to others as well. I'm going to stop here because I have the second part of my presentation where I'll talk about a little bit about more specifics, some of the technical aspects, so you'll understand the data better as far as it relates to untargeted analysis. And I'll give you our update on how we approach now coupling untargeted and targeted analysis using our more recent work that we haven't published yet. So I'll stop here.
Great. Thanks very much, Alexey. Are there any questions for Alexey at the moment? Bill.
I can ask that. When I heard people say that this provides a permanent digital record of a sample, I was under the impression that I understood something from that sentence, but you say it has no meaning. Can you?
Well, it has no meaning to me. What is a permanent digital record? I mean, what digital record, what is more permanent about this digital record than some other record, for example?
So I also
what
agree
is more digital about this record than any other?
So the sentence is kind of silly, but it's, I guess the thought behind it, or the philosophy, is that the data is more complete and therefore more maybe more suitable for kind of iterative analysis, right? There's nothing missing because of DDA stochastic problems. I guess that's the sort of philosophy behind that statement, which I also think is not a good way to put it.
Sample isn't degrading, and it's digital because it's in a computer, right? I mean, that seems like.
Well, but if you do but you want to distinguish DDA. I mean, yes, you're right, but yeah, but by making that sentence, I try to distinguish between DIA and conventional strategies such as DDA, I assume. So if you talk about MS1-based quantification, for example, in shotgun DDA, in DDA workflow, you do have a permanent digital record of MS1 scans, and you can go to MS1 data, and you can, using that library of MS1 MOAZ and retention times, you can find that peptide and you can quantify. So I think I'm not saying that's necessarily a bad sentence. I'm just saying that's sort of a really awkward way to, I think, to put it. You have to think a lot about what it means.
Yeah, I guess you're right, because Ben's point is that it's complete, which isn't even in that sentence.
Right.
And DDA gives you a permanent digital incomplete record.
So it was probably not well put, but this was the idea. Ben.
Did you try, actually, since you have used diffusion for your DIA experiments, to use HCD fragmentation as well as CID fragmentation? And how does Ampere works with these 2 different fragmentation techniques?
We did not try CID in this case because DIA-Ampere would not work as well. I mean, for DIA-Ampere to work well for aligning precursors and for detecting precursors and fragments. Well, precursors, of course, you have high mass accuracy data, but for fragments, if you do CID, the accuracy is not there. So you're just going to have a lot of peak curves extracted from the data, and it's going to be really messy because you start aligning fragments with the precursors, and if you don't have this mass accuracy on a fragment.
He's asking because yesterday I presented stuff by using high mass accuracy. You can use resonant CID and use the Orbitrap to analyze the data.
Oh, okay. I thought you talked about CID and then doing measurement in ion trap. But CID and doing, well, no, we haven't tried that. I don't know what, frankly, if you do CID and then the Orbitrap measurement, I don't think there would be a dramatic difference as far as our strategy. But I don't know about what would be the advantages, but I don't see immediate difference for our computational strategy.
Brent, did you want to?
Sure. So early on, you kind of offered some examples of where you felt prior knowledge had not been useful. And I'm wondering if you would at least admit that I can probably come up with as many examples where prior knowledge is useful.
Of course, that's why I said that that's why I said that I'm exaggerating a little bit on purpose, right?
Okay.
But I think that's also true that when it comes to spectral libraries specifically, this is what we're discussing here, it has not been as useful as initially expected for conventional analysis of mass spec data.
Tina.
Maybe a bit more technical question, but you said that when you generate your pseudospectra, you do not use the intensity as you see it, but you multiply this intensity by the correlation between precursor and fragment, right? Mm-hmm. Isn't that counterintuitive when you then use this other workflow, the hybrid one later on, that your intensities do not match perfectly to your library? Have you checked this? So why are you doing this multiplication step?
Well, first of all, you could turn off that multiplication as a parameter. You don't have to do that. Second, because again, we don't want to create a mass fragment that has very little correlation with the precursor. Somehow it still was within the ppm mass accuracy that we allowed for the database searching, and then we matched that fragment. We don't really want that fragment to be used as confidently as another fragment that has really the right mass accuracy and also the right coelution. In a way, a better way would be to use ion interference tools, like some of these targeted extraction tools, implement complicated logic for calling interferences and see what fragments probably interfered because they don't coelute with other fragments. That would be probably a better way. So this multiplication with a precursor, in a way, what we hope is that if maybe if it doesn't correlate that well with the precursor, it will still make it to the list and will help us to identify the peptide, but maybe wouldn't make it to the list of top and most abundant fragments for that peptide, so it would not be used for quantification. So I know there is a little bit of unsatisfactory feeling about that multiplication. I don't know how much it affects the results. It could be turned off as well, and I don't think it's a dramatic difference that it would introduce, but it's sort of one way that we have of eliminating some of the ions that may be interfered by other fragments of precursors from the consideration for quantification analysis later.
Bill?
So I also had a technical question about you were talking about the incompleteness of the human peptide atlas, and I wondered whether Isa described, this effect where if you start using larger and larger libraries, of course, your number of hypotheses increases, so there's a loss of power just because there's too many things to consider, right? So I wonder whether in the Venn diagram, when there were things that were found when you used a smaller library that weren't found from the larger human peptide atlas, mm-hmm. was that because they weren't in there, or was it because you had a loss of power from the large library and they're actually there, just not identified? We
haven't looked at that. I mean, it's possible that some of them we didn't find because of the library was already large. But remember, what we did find from DIA and DDA, from our runs, was found by searching against the whole proteome database, right? So we did find those peptides by searching a very, very large protein sequence database. The library is already smaller than that database. So I don't think the size of the library is the main explanation of the spectral library, of this pan-human library was the main explanation for not finding that peptide.
Maybe I can, well, I can add one thing. So one thing that might account for some of these missing things is that in this pan-human library, the scoring thresholds at peptide level to be allowed into the library was very, very strict. So, and possibly much too strict. So I think there will be peptides missing from there because of differences in the score threshold or the FDR threshold that we had, that you had in your search or we had in our search. It's because we're running this Mayu tool and we're insisting that every peptide can achieve a protein FDR of 1% independently, right? That makes for a very strict peptide level threshold. So I suspect if you did that Venn diagram at the protein level, the differences will be potentially less large. I think we kicked out peptides, some peptides for proteins because they didn't make this very strict threshold potentially.
It's possible, but also that library was generated using ABSIX 5500 data, I believe, where this was fusion or Q-exactive for fusion data. So I think there is also the library perhaps is a little bit dated by now, that if you regenerate that library, that would be different. Mm-hmm. But I believe that you're always going to be finding something new. Well, maybe in HeLa. HeLa is probably the best example where the previous knowledge was very useful. Mm-hmm. Especially if you buy pre-digested HeLa from Thermo. But for all other samples, I would assume that there would be some degree of incompleteness always, no matter what.
Last question, Tina.
Probably got many times before. But when I'm just listening to your concept, one obvious question for me is, so you're generating a library on data which you use then later on to search for these peptides. So how do you make sure you're not overfitting your data if you just search something that comes from the same data before?
So when we generate that library, we apply false discovery rate analysis. So our library is filtered to say 1% protein FDR and 1% PSM FDR. So, of course, it has mistakes. I mean, that's a false discovery rate analysis. That's what it is. We have 1% of mistakes in that library, right, at the PSM level. But we typically do 1% protein FDR and then 1% PSM FDR. So the PSM level number of mistakes is less than 1%, but the number of proteins would be, say, 1% mistakes. So then we go to the same DIA data. So what we know we're not going to get for sure is we're not going to increase our protein or peptide level false discovery rate at that point because we're not identifying anything new, right? We are only re-extracting quantification information. So our global FDR for the data set will not change. What we have to be concerned about is the criteria that we apply for calling something detected or extracted from a particular run. And in that case, we do have a modeling strategy for assessing the accuracy of quantification, not accuracy of quantification, but accuracy of identification or detection in that specific run. Yes, you still have to do that. But even if you make a mistake, you're basically going to, instead of missing value, you're going to get a false quantification potentially.
You also made the point that you try to be very relaxed in this library generation process, right? That you rather want to have by far too many spectra than too little. So that's why I'm at this point.
No, that's not the case. We are liberal with generating MGF files. Mm-hmm. We are liberal with how many precursor fragment groups we extract from the data. Mm-hmm. But whatever we have goes through rigorous FDR filtering after database searching. So no, the library is generated using a very rigorous way. It's just how the MS, what goes to the database search for searching, that's where we overpredict.